1. And then, no, that's not our equation number 1. Okay, so from here, we're going to make this statement where stress, okay, stress is equal to Young's modulus multiplied by strain. Okay, so this is talking about this line over here. And this is basically Hooke's law. And Hooke's law is where we're going to put in our equation number 1. Okay. Yes, Tony, you have a question.
Yeah, why is the stress negative in here? Is it because it's in compression?
Yes.
Okay, thank you.
So most of the time when we see what is given, right, we always draw. Okay, what is always presented is we are always presented this. Okay, even though it's carried out in compression. Yeah, even though it's carried out in compression, we still draw it this way. Yes or no? Right? Okay, but no. Okay, compression by right we have to draw that quadrant, but for simplicity's sake, we always draw on the first quadrant, not on the third. Okay. Right. So from here, I'm going to address this as equation number 2. Okay. And then I'm going to address this as equation number 3. Okay. So what we're going to do now is we're going to substitute equation number 2 and equation number 3 into equation number 1. Okay. So what we have is minus px over a. So equation number 1, let me write is normal stress is equal to Young's modulus multiplied by strain. Okay. So what we have is minus px over a is equal to E, and the strain is minus delta L over L naught. Okay, minus delta L. So the change in length, okay, so we can write the change in length delta L is equal to px L naught over AE. Okay, so this equation is very familiar. You know this equation. You've seen this equation before in your static analysis. Okay, or sorry, in 2 P04. Okay, now this equation over here is only true, right, if the material is in the elastic region. And more important, material will not buckle. Okay, so the material will not go into buckling, right? So some of you might say, Eugene, how do we know the material will buckle or not buckle? So now the question comes to you is this. Okay, the question comes to you is this. How do we know when buckling will occur? Okay, that's the question, right? You go through compression, then how do you know buckling will or will not occur? Okay, but let's focus on this equation first. Let's focus on equation number 4 first. Okay, let's focus the equation where buckling will not occur. Okay, now, so we have derived a relationship where the change in L is equal to px L naught over what? AE. Now, I'm going to pull you away from structure analysis, okay, and we're going to look at stiffness. Okay, so if we look at stiffness, okay, stiffness, and stiffness, the sign is a small k. Am I right? Yeah, we usually call it a small k, and the unit is Newton per meter. Okay. So just to quickly recall to all of you regarding stiffness, like you asked Eugene, I can't remember what is stiffness. So basically, if you have a structure, okay, and you have a spring, okay, so this is our spring, right, and you apply a force P, okay, we apply a force P, and we realize that the force, I'm going to call this Px, okay, we are going to apply a force Px. So when there is a, when we apply, or initially there's no force, okay, and then if we apply a force, the spring get more compressed, okay, so this is our, this is with a load, okay, this is with our load Px, okay, and the spring has a constant, okay, which is known as stiffness, and as given earlier, is in small k, right? So how they calculate this small k is they specify a certain force, and then there's a change in, for this case, there's a change in our x direction, right? There's a change in x direction. So the stiffness is equal to Px over x distance. Okay, so that's where, that's how you measure it. Okay, so this is Newton per what? Meter. So how do I mean this is how you measure? So what you, how, when you carry out this experiment, I believe you guys have done this in high school before. So stiffness is known as the known load. So you put a known load to the spring, and then you measure the distance moved. Okay. Then you plot this graph. Okay. Then we tend to plot this graph now. Okay. So the graph that we plot. Okay. Probably all of you have seen this before. Then we plot this graph. So we have our x-axis, and then we have our y-axis. So the x-axis is your x distance move in meters, and then over here is your load P, okay, your Px in Newton. So we know the higher load you put, okay, you know that the higher load that you put, the higher the deflection. So over here, this slope over here is your K, your small k, which is your stiffness, is equal to P over X, exactly like what we have over here, or Px over X. So that is your stiffness. Okay. So from here, we know that Px is equal to K stiffness multiplied by what? X. Okay. So this is the X value we're talking about. Okay. So we realize that X is also equal to our change in length, right? In, if we were to go back, change in length in our equation number 4, right? Change in length in equation number 4, right? So in this case, right, change in x, so we are going to equate, so this is, I'm going to call this equation number 5. So if we're going to equate, okay, if we are going to excuse me, if we are going to equate equation 4 and equation 5, okay, so equation, if we go back to equation 4, right, so equation 4, let's see what's our equation 4, is px L naught over AE, okay, so it's px L naught over AE. So this will be equal to the change length is x, is px over k. Okay, so you can get rid of your px. So your stiffness k is equal to AE over L naught. Okay, so this is our equation number 6. Okay, so what you see over here, right, the stiffness is dependent on the cross-sectional area, the original length, and the Young's modulus. Okay, is if we look at units, so this is in if you look at units, this is in meter squared. Over here, this is in Newton per meter squared. And over here, we have meter. You cancel everything. It's also equal to Newton per meter. Okay. So in buckling, okay, so this equation is valid if the structure does not buckle. Okay. So, and this equation is our equation. So in buckling analysis, okay, buckling analysis, the L over A ratio, okay, the L over A ratio is very what? Is very high. Okay. So therefore, equation 6 will not be valid. Okay. So we cannot use this stiffness or this way of deriving stiffness to analyze what? Buckling. Okay. So why is that? Okay. Why it is not valid? The thing is, we will ask why it is not valid. Okay. Why it is not valid? Right. And I'll show you why. Okay. Under non-buckling deformation, right? So for non-buckling deformation, like how we derived earlier, right? So if our structure is like this, and if we put a load, the structure becomes shorter. Okay, so the difference is our delta L over here. So that's not buckling. If buckling, okay, for buckling deformation, the structure will deform this way. When we put a load P over here. So the deformation is not the same anymore. Okay, the deformation is not the same anymore. You might say, Eugene, we still have a deduction in length. Okay, change L. Yeah, but if you look at the deformation, right, the deformation is no more on a straight line. It's a curve now. Okay, so that is why you cannot use axial loading to design a buckling structure. Okay, so the deformation of buckling, you can see over here, the deformation in buckling or in buckling is not parallel to the centroid axis of the structure. Okay, it's not the same. So we have to come out with a different type of analysis. Okay, we have to come up with a different type of analysis. We cannot rely on these formulas. So what formula we cannot rely anymore? Okay, so the formula that we cannot rely anymore is this formula. We cannot say that, yes, we cannot specify that stress is equal to px over a. This is not more valid anymore. And we also cannot use the deflection. Okay, we cannot use the other formula where deflection or the change in length is PL over AE. So it's not valid anymore because of how the structure is deformed. So some of you will say, then how are we going to analyze buckling? Okay, so the solution is not so far from the knowledge that you all know. Okay, so what we're going to do is we are going to apply bending moment relationship. Okay, so that's where we are going to talk about Euler's formulation applied to buckling. Okay, so before I go for buckling based on Euler formulation, let's take a 5 minutes quick break. We come back and we'll carry on. Okay. So we will come back at 8:10.